All right, so I'm going to continue where I left off last time, and I'm going to talk just a little bit more about determinants. So first I wanted to recall if we have an n by n matrix A, we defined the ij cofactor of A, which I denoted as a Cij, and this was defined to be -1 to the power of I plus j times the determinant of the matrix obtained by removing the ith row and the jth column of A. And one of the things that we could do with cofactors is we could use them to calculate the determinant of a matrix A. So you could compute the determinant of A by doing cofactor expansion along the ith row. So that's where you take each entry in the ith row of A, you multiply by the corresponding cofactor, and then you add everything up. And then you could also do cofactor expansion along any of the columns of A as well. So along the jth column, you would take each of the entries of A in its jth column, multiply each of them with their corresponding cofactor, and again, if you add all of that up, it will result in the determinant of A. So just as a small example to start with, to remind ourselves of how it works, here I've got this matrix A written down, and let's just compute its determinant by doing this cofactor expansion. Okay. We can do this using any row or any column of A. I'll start by illustrating with the first row. And before I do that, let me draw a little picture here. So you guys might remember that I drew this kind of a picture last time. This picture of plus and minus signs, what it does is it tells me whether -1 to the I plus j is going to be positive or negative. So that usually when I'm computing cofactors, I'm not actually thinking what is I, what is j, and what is -1 to the I plus j. I'm just thinking, is this going to be plus or minus according to which entry of the matrix I was looking at, okay? So if I'm going to do cofactor expansion along the first row, I'm going to take each entry in the first row, starting with the 2. So I'm going to have 2 times, let's see here, I guess it'll be plus as well, so maybe just to emphasize it, I'll do plus first. 2, and then we're going to cross out the row and the column containing the 2. We have this remaining 2 by 2 matrix. And I'm going to need the determinant of this. Okay. Next, along the first row, we're going to do -3. Okay. And then I'm going to cross out the row and the column containing that 3. I have this remaining 2 by 2, which I'm going to write down here. Okay. After that, we're going to get plus 0 times the determinant that you would get when you cross out the row and the column containing that 0. And you have this 2 by 2 remaining. Okay. And then we need to compute each of these 2 by 2 determinants. So remember the formula for a 2 by 2 determinant is A, D minus B, C. So it'll be -6 minus 1 is -7. And we have -3 times, this would be +3 minus 0. And this would be plus 0. Okay. So it looks like here the final answer is going to be Negative 14 minus 9 is negative 23. Okay. And then just as one more example, to emphasize that you can choose any row or any column to do this, let's say that we choose to expand along the first column instead of the first row. So I would take each entry in the first column now, starting with the 2. So we're going to have like a plus 2 times, then again you cross out the row and the column containing that 2, take what's left in your matrix. And then along the first column, so next we're going to do minus negative 1. So minus and negative will become plus. Then again, I'll cross out the row and the column containing that negative 1. We have 3, 0, 1, negative 3 remaining. Then we're going to get plus 0. And you would multiply by this 2 by 2 determinant, but 0 times anything is 0, so we don't have to write it out. Then we'll compute each of these 2 by 2 determinants. Here, AD minus BC is negative 9. And this gives us the same answer of negative 23 again, okay? So you can choose any row or any column, and you'll get the same answer, and that answer will be the determinant of the matrix A. Okay. So now I want to go over 2 applications of determinants and cofactors right now. So one of the applications I wanted to discuss is a formula for computing the inverse of a matrix. So the way this formula works is if you take each of the cofactors and put them into a matrix C, so let's say C is a matrix of cofactors of A. We have this formula that A times this cofactor matrix C transpose. Turns out that this will be equal to the determinant of A times an identity matrix. I'm not going to prove that, but that is a fact that turns out to be the case, where anytime you take a matrix A and you multiply it by the transpose of its cofactor matrix, that product always results in the determinant of A, this scalar, multiplying an identity matrix. So then if the determinant of A is not equal to 0, then what you can do is you can divide both sides of this equation by the determinant of A. So if I divide both sides by the determinant, on the left, I'm going to group together the 1 over the determinant with the C transpose matrix. Okay. So here we have A times some matrix equals the identity. So therefore, this matrix that we are multiplying A by must be the inverse of A. So you get this formula that A inverse is 1 over the determinant of A, and then times the transpose of its matrix of cofactors. Okay. All right. So I'll illustrate how that formula works exactly with an example as well. So I'm going to return to the matrix that I was using in this example just now. And let's say I want to find the inverse of A. By using its cofactors. Okay. So what I'm going to need to do first is I'm going to need to compute all of the cofactors of matrix A right now. So for a 3 by 3 matrix A, it is going to have 9 cofactors in total. So I'll start by computing the 1, 1 cofactor. So for the 1, 1 cofactor, it's going to be plus, then cross out the first row, the first column. You have this remaining 2 by 2 determinant. If we compute this right now, it's negative 6 minus 1, negative 7, okay? Next, we'll compute the 1, 2 cofactor. So the 1, 2 cofactor is going to be negative. Then cross out the first row and the second column. We have this remaining 2 by 2 matrix. And this determinant is going to be 3 minus 0. So positive 3, but then there's a minus in front, so the cofactor is negative 3, okay? For the 1, 3 cofactor, it's going to be plus. Then cross out the first row, the third column. We have this 2 by 2 remaining. This determinant is going to be negative 1, okay? Next, let's get the 2, 1 cofactor. So second row, first column, it's going to be minus. Okay. And then here, cross out the second row, first column, 3, 0, 1, negative 3 remaining. It's going to be negative 9, but then there's a minus in front, so it'll be positive 9. Okay. The 2, 2 cofactor, it's going to be plus, and then cross out the second row, the second column. We have 2, 0, 0, minus 3 remaining. So that determinant is negative 6. Then for the 2, 3 cofactor, it's going to be minus. Cross out second row, third column. You have 2, 3, 0, 1 remaining. So it's going to be positive 2, but then the minus in front makes it negative 2. Lastly, we'll do C3, 1. It'll be plus. Then cross out the third row, the first column, 3, 0, 2, 1. This determinant is positive 3. C3, 2. So cross out the third row, the second column. Well, okay, so it's minus, and then cross out third row, second column. So you get 2, -1, 0, 1. So that's going to be 2, but then minus in front, so it's -2. And lastly, the 3, 3 cofactor. So it's going to be plus, and then cross out third row, third column. Okay. So we have that 2 by 2 remaining, and then the determinant of this would be 4 minus -3, so +7. So now that we've computed all the cofactors of A, I'm just going to put all of them into a matrix C. And so that was the first row of cofactors. Next we have 9, -6, -2. Lastly we had 3, -2, and 7. Once you get all the cofactors and you put them into a matrix, then as we saw earlier, we have this formula for computing the inverse. So the inverse of A should be equal to 1 over its determinant, and then times the transpose of the cofactor matrix. Okay. So we computed the determinant of A already. It was -23. So A inverse should be 1 over -23 times, and now we have C transpose. So I'm going to take the matrix C over here, the matrix of cofactors, and I'm just going to transpose it. So first row will become the first column here. Second row C is now the second column in the transpose. And the third row C is now the third column in the transpose. Okay. So then this gives us the inverse of the original matrix A. Okay. So that's one small application of determinants and cofactors, is you can use them to calculate the inverse of a matrix. So earlier in the semester, we learned another method of calculating the inverse of a matrix, where you would take A, augment it with the identity. You would do operations until you reduce A to an identity matrix, and then whatever was on the right would be the inverse of A. So that's one method of computing the inverse of a matrix, but there is this other method that you have now involving determinants and cofactors. Okay. Now there's another application of determinants which I want to talk a little bit about, which is a Cramer's rule. Okay. So let me talk a little bit about what Cramer's rule is. So let's say that you have a system of equations ax equals b. And let's suppose that A is invertible. And if you'll recall last time, a matrix being invertible is equivalent to saying its determinant is non-zero. So Cramer's rule, what it does is it gives you a formula for calculating the solution x. And specifically, it gives you a formula for each of the components of x. So it calculates like x1, x2, x3, etc. So the general formula is xi, the ith variable, is equal to the determinant of some matrix, which I'm going to call AI, and then it's over the determinant of A. Okay. Now AI, what this matrix represents is it represents the matrix A. So AI is, well, I'll write it like this. So AI is the matrix obtained by replacing the ith column of A with vector B, where B was whatever you had on the right-hand side of your system of equations. Okay. So I'll illustrate that with how Cramer's rule works with another quick example. So let's say I had the system of equations x minus 2y plus 3z equals -4, 2x plus z equals 6, and then x plus y minus z equals 7. So from the system of equations, we have the matrix of coefficients. That's A. We have the vector of variables x, y, z, so that's vector x. And then vector b, the right-hand side, was -4, 6, and 7. Okay. So if you wanted to solve for x, y, z, normally what you would do is you would set up the augmented matrix, do the elimination, and then some back substitution after that. So I guess as an alternative, you can also calculate x, y, z without doing any row operations at all, and instead using Cramer's rule to calculate them. So here's how Cramer's rule would work in this example. So if I want to solve for x in the system of equations, Cramer's rule tells me that x is going to be and here in the numerator, I have the determinant of the matrix obtained by replacing the first column of A with B. So here's A. I'm going to replace its first column with B over here. So instead of 1, 2, 1, I'm going to do -4, 6, 7. And then I'm going to copy the rest of the columns of A as they are. So again, that's just taking A and replacing its first column with B. So that's what we have in the numerator, that determinant. And then we're going to divide by the determinant of A itself. So now we have to compute each of these determinants. Okay, so let's do cofactor expansion along the along the second column, because I noticed that there's a 0 in that column, which will make it a little bit nicer. So along the second column, I'm going to take minus -2, cross out row and column containing that -2. We have 6, 7, 1, -1 remaining. So I was doing it along the second column, so we had minus -2. Next will be plus 0. And next is going to be -1. And then if I cross out the row and the column containing that 1, got -4, 6, 3, 1 remaining. That's all in the numerator. And the denominator, let's also expand along the second column to get the determinant of a. So we'll do minus -2. Cross out the row and the column. We have 2, 1, 1, -1 remaining. Next will be plus 0. Next will be minus 1. And then cross out the row and the column containing that 1. You have 1, 2, 3, 1 remaining. And then we're just going to finish calculating these 2 by 2 determinants. So this is minus 6 minus 7. So 2 times -13. Here it's -4 minus 18. So it's going to be minus from this. And then this was -22. Down here we have 2 times -2 minus 1, so -3. Minus, and then we have 1 minus 6 is -5. So altogether it's -26 plus 22 is -4. That's all over -6 plus 5 is -1. So it looks like x is going to be equal to 4, okay? Let's do at least one more. So let's say we also wanted to solve for y next. In the system of equations. So of course, again, one way to solve it is to just do the ordinary elimination with back substitution. But here I'm showing you how to solve for x, y, and z by using Cramer's rule instead. So to solve for y, we're gonna take matrix A, and y is the second variable, so we're going to replace the second column of A with vector B. So I'm going to copy down the rest of the columns of A. So this is just A, but the second column, again, has been replaced with B. And then we have to divide by the determinant of A. And then this will calculate y for us, okay? Now, we've already calculated the determinant of A previously. So we know that in the end, determinant of A is -1. Let's calculate the determinant of this matrix in the numerator. There are no zeros anywhere, so let's just expand along the first row this time. So we're going to have plus 1, and then cross out the row and the column. Next will be minus -4, so plus 4. Cross out the row and the column. And then lastly, you're going to get plus 3. Again, cross out the row and the column containing that 3. We have 2, 1, 6, 7 remaining. So let's work out what we have in the numerator. So we have -13. Next we have a plus 4. Minus 2, minus 1, so -3. Plus 3, And here we have 14 minus 6, so 8. Still all over negative 1. So here this is negative 13 minus 12 is negative 25. Plus 24 is negative 1 over negative 1, so y is equal to positive 1, okay? And I guess I'll go ahead and just finish the example. So let's go ahead and just solve for z, might as well. So for z, what we're going to do is now we're going to take a and replace the third column of a with vector b. Okay. But we'll leave the rest of the columns of a as they are. Divide by the determinant of a. And again, we know the determinant of a is negative 1. Here, let's do cofactor expansion along the second column because we have a 0 in there. So I'm going to do minus negative 2 plus 2. Remove the row and the column. Okay. Next, it'll be plus 0 going along the second column. Next will be minus 1. Cross out the row and the column. We have this remaining. Okay. So we have 2 times 14 minus 6 is 8. Minus 6 minus negative 8. So 6 plus 8 is 14. All over negative 1. That's going to be 2 over negative 1 is negative 2. Okay? So then altogether, from Cramer's rule, we solved the system of equations, x equals 4, y equals 1, z equals negative 2. Okay. And if you want, you can plug these numbers in for x, y, z just to confirm that everything works out. So example, 4 plus 1 minus negative 2 is in fact equal to 7. 2 times 4 is 8, plus negative 2 is 6, and etc. Okay? So that's how Cramer's rule works. Okay. Let's move on to the last topic for this review. So I'm going to begin talking about eigenvalues and eigenvectors a bit. Okay. So eigenvalues and eigenvectors, just like determinants, these are only defined for square matrices. So let's suppose that we have like a square matrix A. Here I've given the definition of eigenvalue and eigenvector. So a scalar lambda is an eigenvalue of matrix A if there exists a non-zero vector x such that ax is equal to lambda x. Any such vector x is then called an eigenvector of A, corresponding to the eigenvalue lambda. Okay. So that's the definition, and I'm just going to be working through some examples of computing some eigenvalues and eigenvectors of some matrices. And then at the end, I'll mention a couple properties of eigenvalues and eigenvectors as well. First, I want to say one thing about the definition here, which is in the definition, you may have noticed that we require x to be a non-zero vector. Reason being because if x were equal to 0, then both sides of the equation would be 0, so both sides would be equal. So x equals 0 is kind of like a trivial solution to this. So to get something interesting, we want to require x to be non-zero, okay? So just as a quick example, I have this matrix A written out here. And what I want to do with this example is just to notice that if we take this matrix A, and let's say I multiply this matrix A with the vector 1, 1, 1. So don't ask why I'm doing that. I just want to do this to illustrate something. So if we multiply it out, you're going to get 1 plus 1 plus 1 is 3. Here we'll get 2 plus 3 minus 2, which gives us 3. And then here we're going to get 5 minus 3 plus 1, which is going to be equal to 3, okay? So this matrix A, multiplying the vector 1, 1, 1, returns 3, 3, 3, which is 3 times the vector 1, 1, 1, okay? So we have A times a non-zero vector x equal to some scalar multiple of that same vector x. Okay? So what this shows us is that 3 is an eigenvalue of this matrix A. And we also see that 1, 1, 1 is a corresponding eigenvector then. Okay? Because we have ax equals 3x, so that's like ax equals lambda x, so the lambda is the 3. Okay? And then the vector x was 1, 1, 1, so that vector 1, 1, 1 was a corresponding eigenvector. Okay? All right. Now, how to find eigenvalues and eigenvectors of a matrix in general. So based off the definition, what we have to work with right now is we have this equation ax equals lambda x, x being a non-zero vector. And what I'm going to do is I'm going to rearrange this equation a little bit. So I'm going to minus the lambda x over to the left-hand side. So this equation is going to become ax minus lambda x equals 0. Okay. You could also minus the ax over to the other side instead, and you can do lambda x minus ax equals 0. So it doesn't matter how you do it. But what I've seen is that most classes move the lambda x over to the other side and write it as ax minus lambda x. So I'm going to follow what most classes here at UTD seem to be doing. Okay. Now here I'm going to factor the x out from both terms on the left-hand side. Now here's something a little bit subtle happens when I factor out the x. So here, when you factor out the x, it kind of looks like you would be left with a minus lambda. Okay. However, this is not quite correct because A is a matrix. And remember, lambda, the eigenvalue, is a scalar. So when you have a matrix minus a scalar, that doesn't make any sense. Okay? That's undefined. We can't do that. So to fix this problem, we're going to insert an identity matrix over here as well. So first, if you redistribute the x back into the parentheses, remember that I times x is still equal to x. So therefore, when you distribute the x, you do get ax minus lambda x again. But by inserting the identity matrix here, now we're going to have a matrix minus a matrix, and that does make sense. That is defined, okay? And now at this point, we have something interesting going on here. So keeping in mind that x was a non-zero vector, and we have a minus lambda I x being equal to 0. So this tells us that the null space of a minus lambda I is non-trivial because we have a non-zero vector x in the null space of this matrix. And if the null space of a matrix is non-trivial, that is equivalent to saying that your matrix is not invertible. So this matrix A minus lambda I turns out to be singular or not invertible. And as we talked about earlier with determinants, for a matrix to be non-invertible, that is equivalent to saying that its determinant is equal to 0. Okay. So what this shows us is that if lambda is an eigenvalue of A, then the determinant of A minus lambda I must be equal to 0. So this gives us an equation to calculate to solve for the eigenvalues of A. Okay. Okay. So to find the eigenvalues of A, what you want to do is you want to calculate the determinant of A minus lambda I, set it equal to 0, and solve for lambda. We'll do some examples so you'll see how that works. Okay. But this is how we're going to be calculating the eigenvalues of matrices in this class. So that answers the question of how to find the eigenvalues of a matrix. As for how to find the eigenvectors, so going back up to here, remember that x was an eigenvector. And what we see here is that if x is an eigenvector, it's going to be in the null space of A minus lambda I. So essentially, to find the eigenvectors of A corresponding to the eigenvalue of lambda, you want to find the null space of A minus lambda I. Okay. So to get the eigenvectors of A, you just need to find the null space of A minus lambda I. And then to be more specific, to find the eigenvectors of A corresponding to lambda, find the null space of A minus lambda I. Okay. So just to introduce a little bit of terminology, null space of A minus lambda I, this is also called the I guess, the eigenspace corresponding to lambda, because it's kind of like a space of eigenvectors of lambda. Okay. So whenever they talk about the eigenspace of a matrix, they're referring to the null space of A minus lambda I, lambda being one of the eigenvalues. Okay. Okay, so let's do a couple of examples to get a better sense for how exactly this works. We'll start with a 2x2 example first. We'll do some 3x3s as well. Okay. So then to get the eigenvalues of A, and then also the eigenvectors, that's the goal. So first to get the eigenvalues, I'm gonna calculate the determinant of A minus lambda I. Okay, so here's how that's gonna work. So remember A, well, we have A is 2, 1, 1, 2. Now I, the identity matrix, remember it just has ones on the diagonal and zeros everywhere else. But since we're multiplying it by lambda, then instead of ones on the diagonal, it's going to be lambda times 1, so just lambda on the diagonals. So we're left with calculating the determinant of this matrix 2 minus lambda, 1 minus 0, 1 minus 0, and 2 minus lambda. Okay. And then just calculating this determinant is AD minus BC. So it's going to be 2 minus lambda all squared minus 1. Okay. And then we're going to take this and we're going to set it equal to 0 now. Okay. So then what I can do is to solve for lambda. In this case, I can just move the 1 over to the other side. So if we square root both sides, there are two solutions. So 2 minus lambda could be plus or minus the square root of 1, which is still 1. So then solving for lambda, we could maybe multiply both sides by negatives to get lambda minus 2 equals, and here still be plus or minus 1, the two possibilities. And then if we add the 2 over, you'll get lambda could be negative 1 plus 2, just 1. Or lambda could also be positive 1 plus 2, which gives us another eigenvalue of 3. Okay. So this matrix A that we calculated just now has two eigenvalues, 1 and 3. Okay. Next, we wanted to find the eigenvectors as well. Okay. So to get the eigenvectors, we now want to look at the null space of A minus lambda I, and we need to do this for each eigenvalue lambda that we found. So we have two eigenvalues here. Let's just start with the first one that I have written down, lambda equals 1. So A minus lambda I, lambda being equal to 1. Okay. So earlier we calculated a minus lambda I up here, and we're just going to plug in 1 for lambda. So plugging in 1 for lambda will give us 1, 1, 1, 1. So to find the null space of this matrix, I guess normally what you do for null space is you row reduce your matrix to row echelon form. Okay. And then at this point, what I do is I take what we have in the row echelon form, I convert it to a system of equations. So we have like 1x plus 1y. We set it equal to 0 because we're looking for the null space. Here, the second column is missing a pivot, so that makes y the free variable. And the way that I would tend to do this is I would assign a parameter t to the free variable. Then I could say x is negative y, or in terms of t, negative t. So then the null space of A minus 1i, which is the eigenspace of A, corresponding to eigenvalue of 1, so it's all multiples of the vector negative 1, 1. Okay. So this would be the eigenspace of A. If they want a basis for the eigenspace, the basis would just be this one vector negative 1, 1 by itself. And the problems, they will tend to only care about finding a basis for the eigenspace. Here, I'll kind of mention like one little subtlety, which is if you want to specify exactly what the eigenvectors were, the eigenvectors would be the non-zero multiples of this vector negative 1, 1. Okay. The reason why we specify the non-zero multiples is because if we go back to the definition of an eigenvector, in the definition it is required that the vector be non-zero. So the eigenspace is not quite the same as the eigenvectors themselves, because the eigenspace does contain the zero vector when t is 0, but the eigenvectors do not include the zero vector. So it's like all multiples of negative 1, 1, but without t equals 0. Okay. That's kind of a small subtlety that I thought I would highlight, but most of the times what people care about is a basis for the eigenspace, so I don't think you need to worry about that too much. Okay. All right. So we found the eigenvectors or the eigenspace for lambda equals 1. But to finish the problem, we also need to do it for lambda equals 3 as well. So next, when lambda equals 3, we also have to compute a minus 3i now. So the simplest way to do that is to take what we calculated for a minus lambda I, and we're just plugging in 3 for lambda. So when you plug in 3 for lambda, it's negative 1, 1, 1, negative 1. Then again, we're looking for the null space of this matrix now. So I guess, again, to get the null space, you typically do row echelon form first. That leaves me with negative 1x plus 1y equals 0. We'll choose y to be free. And then if y is equal to t, then x is equal to y, so that x would be equal to t as well. So then the eigenspace of A corresponding to lambda equals 3 would be the multiples of the vector 1, 1. Really, you typically only care about getting a basis for the eigenspace. So in that case, the basis for the eigenspace, or at least a basis for it, would be just the vector 1, 1 by itself. The actual eigenvectors would be the non-zero multiples of 1, 1. You could write it like that, okay? All right. So that was an example of getting the eigenvalues and the eigenvectors for a 2x2 matrix. So let's note a couple of things before we continue to another example. So when you do A minus lambda I, because the identity is just ones on the diagonal, so lambda I is just lambdas across the diagonal. So when you do A minus lambda I, you're essentially just going to minus lambda across the diagonal of A, okay? So then, rather than kind of like always writing out A minus lambda I like this, you can kind of skip just straight to here by subtracting lambda from each of the diagonal entries of A, okay? Another thing that I want to observe right now in this example is when we computed the determinant of A minus lambda I, for a 2x2 matrix, we ended up with a quadratic or second degree polynomial in lambda. So in general, when you compute the determinant of A minus lambda I, this is going to be an nth degree polynomial in lambda, assuming that A is an n by n matrix. So this nth degree polynomial that you get by computing determinant of A minus lambda I, this is called the characteristic polynomial of A. Well, okay, that's close enough, I guess. I guess it could be plus or minus the characteristic polynomial, but that's okay. Okay. So then the roots or the zeros of this polynomial are the eigenvalues of A. So you can say that the eigenvalues of A are the roots of its characteristic polynomial. Okay. So that's just introducing some terminology that you might encounter. So let's go ahead and do more examples. So let's come over to here next, and I'll do another quick 2x2 example first, and then I'll also do some 3x3s. So I wanted to look at this matrix next. It's almost the exact same as the matrix in the previous problem, but I made a small change where I did put a negative on this entry, okay? So let's see what happens when we try to calculate its eigenvalues again. So I'm going to do determinant of A minus lambda I. So I'm going to subtract lambda from the diagonal entries of A. Here when we do the determinant AD minus BC, so minus and negative 1 is plus 1. And then I'm going to set it equal to 0 now to solve for the eigenvalues. And let's say if I wanted to solve for lambda, so maybe I'd move the 1 over, so you get 2 minus lambda squared equals negative 1. And then let's say we would try to square root both sides next to try to solve for lambda. And when we do that, you'll notice that you're going to end up taking the square root of negative 1, which will lead to getting some imaginary numbers. Okay. So this matrix A has no real eigenvalues. It does have some imaginary eigenvalues though. But in this class, we are not going to do anything with complex eigenvalues. Okay. So if you have a situation like this where you have no real eigenvalues, then you would just stop. There's nothing else you can do since you have no real eigenvalues. You're not going to be finding any eigenvectors since you don't have any real eigenvalues, okay? All right, so then that's it for that example then. So one thing to notice then is that if we only care about the real eigenvalues, then not every matrix will have eigenvalues in the first place if we only care about real ones. And therefore, not every matrix will have eigenvectors either. Okay. Let's do a 3x3 example next, okay? Okay. So again, we're going to start by calculating the determinant of A minus lambda I. So A minus lambda I amounts to subtracting lambda from each of the diagonal entries of A. Okay. Everything else will remain the same. Okay. Now it's a little bit more complicated then because we have to compute this 3x3 determinant. So I'll compute it by doing cofactor expansion. I'll just do expansion along the first row. So along the first row, we had this plus, minus, plus alternating pattern. So along the first row, I'm going to start with plus 2 minus lambda. Okay. Remove the first row and the first column. We have this 2 by 2 remaining. Next, we're going to do minus 1. Cross out the row in the column containing that one. We have 1, 1, -2, -1 minus lambda remaining. Then we're going to get plus -1, so -1 again. Cross out the row in the column containing that -1. Take what you have remaining. And now we have to continue working out each of these 2 by 2 determinants. So here we have 2 minus lambda times, let's multiply this out. So you're going to do AD minus BC. I'm going to go ahead and FOIL out A times D. So it's going to be -2 minus 2 lambda plus lambda and plus lambda squared. So that's A times D FOILed out. And then we have minus BC. So minus -2 is +2. Looks like the -2 and the +2 will cancel, so that's pretty nice. Next, here we have minus. AD gives us -1 minus lambda. Minus a -2, so +2. Minus AD minus BC. So minus 2 minus lambda in parentheses. Okay, so let's continue simplifying. So 2 minus lambda. Here we have lambda squared. And then minus 2 lambda plus lambda is minus lambda remaining. Here, this is 1 minus lambda if you combine the -1 and the +2. And here we're going to get plus lambda 1 minus 2, so plus lambda minus 1. Okay. So incidentally, these terms are going to cancel out. Okay. So what we really have is 2 minus lambda. And then lambda squared minus lambda, we can factor a lambda out from these 2 terms. That leaves us with lambda minus 1 remaining. Okay. So then if we set this equal to 0, we get eigenvalues of 2, 1, and 0. Okay. So it gets more complicated for 3 by 3 matrices. The determinant is a little bit more work to compute. And you get a cubic polynomial, so it could be difficult to try to factor it and find the roots as well. But in this case, we were able to factor it pretty nicely. Got these eigenvalues. So then the next step is to get the corresponding eigenspaces for each of the eigenvalues. Let's start with lambda equals 2 first. So when we look at a minus 2I, let's plug 2 in for lambda for a minus lambda I over here. When lambda is 2, that's going to be negative 3. Okay. So then we want to find the null space of this matrix, because the null space will give us the corresponding eigenspace. So we want to do some row reducing right now. I think I'll start by swapping row 1 and row 2. Next we can do row 3 minus row 1. Then if we do row 3 minus row 2, okay. So now that we've reduced A to row echelon form, in fact this is actually the reduced row echelon form, I get these two equations. X minus 2z is 0, y minus z is 0. In this case, the third column is missing a pivot, so we're going to make z our free variable. So let's say z equals t. So then y equals z, so we can say y equals t. X equals 2z, so x equals 2t. Okay. So then if we take the coefficients of t, 1, 1, this will give us a basis for the eigenspace. Corresponding to its eigenvalue, in this case for lambda equals 2. Have to do the same for lambda equals 1 and lambda equals 0. So for lambda equals 1, a minus 1I. So here's a minus lambda I, and you can just plug in 1 for lambda. We want to find the null space, so let's start doing some elimination. Okay. So then this would be a row echelon form of A. So this would be good enough to stop to get the null space. So we're left with these two equations. And in this case, our two pivots are here and here. So actually the second column is missing a pivot. So that would suggest that we let y be our free variable instead. So y is t. We have here z must be 0. And then with z being 0 and y being t, you'll get x is equal to negative t. So taking the coefficients of t gives us the vector negative 1, 1, 0. And this would be a basis for the eigenspace. Of A corresponding to lambda equals 1. So I won't write all of that out, but here's the basis for the eigenspace when lambda is 1. Okay. Lastly, we need to look at when lambda is 0. So it's just A minus 0i. So it's just the original matrix A. So to find the null space, we'll do some row operations first. I swapped rows just because I prefer having one as a pivot. Okay. Here, I think it's not a big deal, but I'll go ahead and eliminate everything above and below the next pivot. So kind of going for that reduced row echelon form because I figure why not. Okay, so I think we were left with that. I guess I meant to do row 3 plus row 2, not minus. Okay. So then from here we get the first row gives us x equals 0. Second row gives us y minus z is 0. Pivots in the first two columns, let's make z the free variable. So y equals z, so y is t, x is 0. So taking the coefficients of t will give us a basis for the eigenspace for the eigenvalue of 0 for matrix A. Okay. Okay, so let's continue. So I want to look at a couple more examples. Here's the next example I wanted to look at. And it's been a while, so I think I won't work through this entire example, but I'll work through just part of it because I wanted to illustrate something with it, okay? But I don't think I want to be here forever. So let's start by computing the determinant of A minus lambda I to get the eigenvalues. So first A minus lambda I, that's got a minus lambda along each of the diagonal entries of A. Then we're going to calculate the determinant. Fortunately, there's some zeros in this matrix, making it a little bit nicer. Let's do cofactor expansion along the first row. 3 minus lambda, cross out the row and the column. And next would be minus 0 and then plus 1. Then we have this 2 by 2 remaining. Okay, so then if we compute these 2 by 2 determinants, we get AD minus BC. Okay. Here we get 0 minus 2 minus lambda. Looks like here we could factor a 2 minus lambda out from both terms. That leaves us with 3 minus lambda squared minus 1. Okay. This is a good enough place to stop to set it equal to 0. So we're going to get lambda equals 2 as one of the eigenvalues, and then over here, if we set this part equal to 0 and continue solving for lambda, it's adding 3 over negative 1 plus 3 is 2, and then positive 1 plus 3 is 4, okay? So here, this example introduces something a little bit new, which is we have a repeated eigenvalue. So lambda equals 2 is like repeated twice. So you have only 2 distinct eigenvalues, 2 and 4. You might hear some people say that lambda equals 2 is an eigenvalue with algebraic multiplicity 2. Okay. Referring to the fact that lambda equals 2 was repeated twice as an eigenvalue when we were finding the roots of the characteristic polynomial. Okay. I don't think you guys really use this terminology of algebraic multiplicity, but I thought I would maybe mention it just for the sake of it. Okay. So then here, to get the corresponding eigenvectors now, you only need to check these 2 eigenvalues. You can't really like check lambda equals 2 twice, so Here it's maybe a little bit nicer then because you only have to do a minus 2i and a minus 4i now to find the eigenvectors. And I'm just going to do when lambda equals 2, but to save myself some time, I won't work through when lambda equals 4, okay? So let's look at a minus 2i specifically. So a minus 2i, we'll just plug in 2 for lambda, and a minus lambda I. If we do a quick row operation, that would reduce things to the reduced row echelon form. And remember that we're looking for the null space to get the eigenvectors. So here we really have only one equation. And there's only one pivot in this reduced row echelon form. So both the second column and the third column are missing a pivot, so we have two free variables. So let's say y equals s, z equals t. Solving for x is negative z, which is negative t then. So then if we write this out, kind of the way that we usually do, using the parameters as coefficients of a linear combination. Coefficients of s are 0, 1, 0. Coefficients of t are negative 1, 0, 1. So in this case, the eigenspace of A corresponding to the eigenvalue lambda equals 2. And let's just write out a basis for the eigenspace. The basis would just consist of these two vectors that we found. Okay. So here I kind of wanted to highlight something new that happens in this example, which is we have a repeated eigenvalue, in this case lambda equals 2. And this is the first time that we've seen an eigenspace which was more than one dimensional. So in all the previous examples, all of the eigenspaces were one-dimensional because there was only one vector in all of those bases for all those eigenspaces. So this is the first time where we've seen an eigenspace that was two-dimensional. And it's kind of happening because we had lambda equals 2 being a repeated eigenvalue. So that can sort of allow for a higher dimensional eigenspace when that happens. Okay. You can also do a lambda equals 4. So find the null space of a minus 4i. You'll end up with a one-dimensional eigenspace for lambda equals 4. Okay. But to save myself some time, I'm not going to do that. I'm just going to do one more example looking at a 3x3 matrix, and then I'm going to finish the review just by talking about some properties of eigenvalues and eigenvectors. And again, for this example, I'm not going to work through the whole thing, but I just want to do part of it just to make an observation. So for this matrix, let's do a determinant of a minus lambda I again. Oops. So we're going to subtract lambda from each of the diagonal entries because we're subtracting lambda I. Now for this problem, this matrix that we have here, or even this one, it is an upper triangular matrix. So you might remember that the determinant of a triangular matrix is the product of its diagonal entries. So just multiplying the diagonal entries together, we're going to get 1 minus lambda cubed, okay? So when we set this equal to 0 to try and find the eigenvalues, this time there's only one distinct eigenvalue, lambda equals 1, okay? And you could say that in this example, the eigenvalue of 1 has an algebraic multiplicity of 3, since it's like a root of multiplicity 3 in this equation because of the power of 3, okay? So if I want to find the eigenspace now corresponding to lambda equals 1, so I guess I'll write out what I just said. So again, I don't think you guys use this terminology that much, but we can see the algebraic multiplicity of this eigenvalue would be 3, okay, because of the power of 3 that we had here. So it's a root of multiplicity 3. Let's try to find the eigenspace now. So we'll do a minus 1i. And we want to find the null space of this matrix. Now here this matrix is already in reduced row echelon form, so there's no need to do any row operations. Pivots are here and here, so the first column is missing a pivot, which would make x the free variable. Okay. So we'll say x is equal to t, and then each row gives us an equation y equals 0 and z equals 0. Okay. So in this case, we have a single vector 1, 0, 0, serving as a basis for the eigenspace. Of this matrix when lambda equals 1. So I kind of wanted to contrast this example with the one that we saw previously. So in this case, we had the eigenvalue 2, which had algebraic multiplicity 2. And you notice that its eigenspace was two-dimensional. Okay. But in this case, we have an eigenvalue of algebraic multiplicity 3. But its eigenspace was not three-dimensional, as you maybe might have expected. Because like here, algebraic multiplicity 2, eigenspace two-dimensional. But here, algebraic multiplicity is 3, and eigenspace is not three-dimensional. In fact, it's only one dimension, okay? One-dimensional. So I'm not going to talk too much about that right now. I'll talk a little bit more about it in the next review instead. But I'll kind of say that in a situation like this where the eigenspace for its dimension doesn't match the algebraic multiplicity, that's kind of bad for reasons that we'll talk a little bit about next time, okay? Whereas when the eigenspace, when its dimension matches the algebraic multiplicity of the eigenvalue, that's kind of a good thing. So we'll talk more about that next week. But to end this review, which has been going on for quite a while, I do want to mention a couple facts about eigenvalues and eigenvectors to round things up. So first thing that I will do is first let's recall what the trace of a matrix was. So the trace of a square matrix is equal to the sum of its diagonal entries. This may not have really been covered much in your class, but it kind of appeared in maybe one or two of your homework problems during the semester. So one of the facts about eigenvalues that I wanted to mention is that the trace of a matrix A happens to be equal to the sum of the eigenvalues of A. Here, when we're doing the sum of the eigenvalues, that includes like I guess like repeated eigenvalues. So you want to include like repetitions. Now I'll illustrate what I mean when I look at some of the examples that we've done already. Another fact that I want to mention is that the determinant of A happens to equal the product of the eigenvalues of A. Again, that includes repeated eigenvalues. So let's test what I've just stated by looking at the examples that we've done in this video. So the trace, which is the sum of the diagonal entries, we're saying is also equal to the sum of the eigenvalues. And the determinant happens to be the product of the eigenvalues. I'm not going to prove this, but let's confirm this is true in the examples that we've done. So I'm going to come all the way back to this very first example that we did. So for this matrix A, the trace of A, so remember it's the sum of the diagonal entries. So in this case, it would have been 2 plus 2, so the trace is 4. If we do the sum of the eigenvalues, eigenvalues were 1 and 3. So we see that they sum to be equal to 4. So the trace of A was equal to the sum of the eigenvalues of A. If we compute the determinant of this matrix, it's 4 minus 1, so 3. If we compute the product of the eigenvalues, 1 times 3 is 3. Okay. So the trace equals the sum of the eigenvalues, the determinant equals the product of the eigenvalues. Okay. Let's confirm that works out in another example. This one had complex eigenvalues, so let's not worry about this one then, because we don't care about complex eigenvalues in this class at least. So let's look at maybe this example next, okay? So if we look at the trace of A right now, so again, trace is the sum of the diagonal entries. So if we add 2 plus -1, the trace is 3. If we sum the eigenvalues, 2 plus 1 plus 0, we get the same answer. So trace of A equals the sum of the eigenvalues. When you look at this matrix, notice that the third column was a multiple of the second column. Okay. So specifically it was negative of the second column. So that tells us that this matrix A is actually not invertible. And remember, if a matrix is not invertible, its determinant must be equal to 0. Okay. On the other hand, so determinant of A is 0, and then if we look at the product of the eigenvalues this time, if you multiply the 3 eigenvalues together, the product is 0. Okay, so determinant of A matches the product of the eigenvalues. Maybe we'll just confirm it once more looking at this example. All right, so for this matrix, the trace of this matrix traces the sum of the diagonal entries, so 3 plus 2 plus 3 equals 8. If we look at the sum of the eigenvalues, this one is going to be 2 plus 2 plus 4. So notice I am adding 2 twice because it was a root of multiplicity 2, the characteristic polynomial. And that gives us 8 as well. So once again, the trace of A matches the sum of its eigenvalues. So notice that you have to include repetitions when you're doing the sum of the eigenvalues. Next, let's look at the determinant of this matrix real quick. Let's just compute the determinant by doing cofactor expansion along the first row. So along the first row, we get 3, 2, 0, 0, 3. And the last one will give us plus 1 and 0, 2, 1, 0. Three times 6 minus 0 minus 2. Sorry, plus 1, and then times 0 minus 2. So that's going to give us 18 minus 2 is 16. And then the product of the eigenvalues is 2 times 2 times 4. So again, you have to include that repetition, but we get the same answer. So again, determinant of A is the product of its eigenvalues. That is always the case for any square matrix, okay? So that's one of the facts that I wanted to mention. And then the last thing I want to note is let's see here. There's one more fact I want to mention. So to do that, I want to introduce a little bit of like notation / terminology. So let's suppose that we have some polynomial. I'll just do like a specific example. It doesn't have to be abstract, or we can do something concrete. So let's say we have a polynomial, any polynomial. I just made one up at random right now just to illustrate. Then let's say that we have a square matrix A. So we can define a matrix P of A using this polynomial and the matrix A. So P of A is kind of what you might expect if you just kind of like plug A in for T in the polynomial here. Be like 2A cubed minus 3A squared plus 1A, I suppose, right? Now, here it would be wrong of us to say plus 4 at the end. Because again, here we have an issue where we're like adding and subtracting matrices from each other. And then we're going to add like a number at the end. And you can't like add a number to a matrix. So to make things make sense, we will again just tack on an identity at the end. So to make that a matrix so that you can then add and subtract everything together, okay? All right, so yeah, given a polynomial, you can take a matrix A and get a new matrix out of that by sort of plugging A into the polynomial. And to be clear, if you plug in a square matrix A, you can calculate A cubed, you can calculate A squared, you can add and subtract, combine everything together. So at the end, P of A is going to be another matrix. In fact, it'll be another matrix the same size as A, okay? And you can do this for any polynomial and any square matrix. Okay, so I want to mention some facts about these like polynomial matrices, if you will. Before I get to that specifically, I want to mention a couple other things. So I'm going to state maybe 3 facts, I suppose. So the first fact I want to state is if X is an eigenvector of some matrix A with a corresponding eigenvalue lambda, then X is also an eigenvector of a to the k, and it'll have a corresponding eigenvalue lambda to the k. Okay. So to kind of illustrate why that would be true, so let's suppose we have x as an eigenvector with a corresponding eigenvalue of lambda, so that ax would be equal to lambda x. Now let's say I multiply both sides of the equation by a again. Okay. So on the left, we're going to get a squared x. On the right, the lambda is a scalar, so you can pull it out to the front and say this is lambda times ax. Okay. But then we know that ax is lambda x again. So that gives us a squared x is lambda times lambda x, or lambda squared x then. Okay. So what this shows us is that if x is an eigenvalue of a with corresponding eigenvalue lambda, then x is also an eigenvector of a squared with a corresponding eigenvalue lambda squared. Okay? And you can generalize that for any other power of a. So like lambda cubed would have been an eigenvalue of a cubed, and etc. Okay? That's one of the properties I wanted to mention. And then another property or fact I want to mention is let's say if x is an eigenvector of a with an eigenvalue, corresponding eigenvalue lambda, then x will also be an eigenvector of a plus any multiple of the identity matrix, and it'll have a corresponding eigenvalue of lambda plus k. Okay. And I'll kind of illustrate with a little example of how that works. So assuming that, again, x is an eigenvector of a with an eigenvalue lambda. If we look at a plus some multiple k of the identity matrix, so a plus ki times x, okay? So if I distribute the x into the parentheses, it will be ax plus k times ix, and ix is just x, since I is just the identity matrix. And then, since ax equals lambda x, this is lambda x plus kx now. Or I can rewrite it as lambda x plus kx. And then I can factor an x out from the two terms, leaving us with lambda plus k. Lambda and k are scalars, so that addition makes sense there. So we started with a plus ki times x, and we saw that was equal to lambda plus k times x, okay? So the idea is this equation it has the same form of ax equals lambda x, except the matrix is not A, but A plus ki, and the lambda is not lambda, but lambda plus k. So if x was an eigenvector of A with an eigenvalue lambda, then x is also an eigenvector of A plus ki with a corresponding eigenvalue lambda plus k. All right? The last fact I want to mention, and then I'll kind of end with a quick example. So the last fact I want to mention is it's kind of a combination of these two facts together. But if x is an eigenvector of A with eigenvalue lambda, then x is also an eigenvector of p of A for any polynomial p. And it'll have a corresponding eigenvalue p of lambda. Okay. And let's kind of get a better sense for what all these facts mean with a quick example then. So let's say that we have a matrix A we're not given exactly what this matrix A is, but we are given that A has eigenvalues of -2, 1, 3. So those are the eigenvalues of A, okay? Now, if we wanted to find the eigenvalues of A squared, according to this first property, the eigenvalues of A squared should be the eigenvalues of A, but squared. So if I just take each of the eigenvalues of A and I square them, those will be the eigenvalues of A squared, okay? You can do that for any other power of A as well. Okay? If we wanted to find the eigenvalues of A plus 5 times an identity matrix, then according to the second fact, whatever the eigenvalues of A were originally, with k being equal to 5, if I just add 5 to all the eigenvalues, that will give me the eigenvalues of A plus 5i. So these were the eigenvalues of A, and I'm just going to add 5 to each of them. So 3, 6, and 8 would be the eigenvalues of A plus 5i. And then to illustrate the third property, let's say we wanted the eigenvalues of 2a cubed minus 3a plus 4i. Okay? Okay, so this over here is a polynomial of a, where the polynomial, the corresponding polynomial is at 2t cubed minus 3t plus 4. Okay. So what this third property is saying is we have this polynomial in A. So the eigenvalues of that polynomial of A should have eigenvalues p of lambda, where lambda is one of the eigenvalues of A. So that means what I should do is I should take this polynomial that we have associated with this expression, and to get the eigenvalues of this matrix, if I take the eigenvalues of A and plug them into the polynomial, so here were the eigenvalues of A, negative 2, 1, 3, and I'm going to plug each of them into this polynomial. So starting with negative 2, that's going to be negative 16, plus 6 is negative 10, plus 4 is negative 6. We plug 1 in for t, that's going to be 2 minus 3 plus 4, which is 3. And if we plug in 3 for t, that's going to be 2 times 3 cubed minus 3 times 3 plus 4. It's 20, 54, 45, 49, if I did my math correctly. So then these would be the eigenvalues of this matrix here, okay? So to get the eigenvalues of a polynomial in A, just take the eigenvalues of A and plug them into that corresponding polynomial. Okay, that's what the third factor is saying. Okay. And I guess I'll just say one final thing, and that will be it. Just one last fact. So we know that a matrix is singular or not invertible if and only if its determinant is 0, right? But we also talked about how the determinant is the product of the diagonal, that the determinant of a matrix is equal to the product of its eigenvalues. So for the product of the eigenvalues to be equal to 0, that's equivalent to saying that one of the eigenvalues was 0. So you can say that a matrix A is singular or not invertible if and only if 0 is one of its eigenvalues. And likewise, you can sort of flip that and say that A is invertible or non-singular if and only if 0 is not an eigenvalue of A. Okay. So that's it for this video, and we'll talk a bit more about eigenvalues and eigenvectors next time as well.